When astronomers talk about Proxima Centauri, they call it our closest neighbor, the star next door, as if we could hop across space the way you'd walk across a street. The word neighbor makes it sound friendly, reachable, even familiar, but this is one of those comforting lies hidden in plain sight. Because the truth is far darker. Proxima Centauri is close only in cosmic terms. For humans, it might as well be an unreachable prison on the far side of infinity. That distance isn't measured in footsteps or highway miles. It is measured in years of light itself, and even light, the fastest thing we know, struggles to cover the gap. It races at 670 million miles per hour, enough to loop Earth 7 times in a single second. And yet, even at that impossible velocity, it needs more than 4 years to travel from Proxima Centauri to your eyes. 4 years of constant speed, 4 years without rest, 4 years across a black ocean filled with nothing. Think about that. You blink, and light circles Earth. You wait, and light still hasn't finished its journey across the short gulf between our sun and its nearest neighbor. That's how empty the universe really is. We are so used to thinking of distance in human terms. Drives that take hours, flights that take days, voyages across oceans that span weeks. But space laughs at those scales. The numbers are too big for our minds to process directly, so we shrink them into comparisons. Imagine Earth as a marble resting in New York City. Now imagine Proxima Centauri as another marble, not in Boston, not even in California, but in the middle of the Pacific Ocean. Between them lies nothing. No rest stops, no gas stations, no islands, just a void so absolute it could swallow 1 million solar systems without letting their stars even brush against each other. That is our so-called neighborhood. And if the numbers don't crush you, the time will. NASA's fastest spacecraft, New Horizons, blasted past Pluto after 9 years of travel, a triumph that made headlines. But at its record-breaking speed, the journey to Proxima would still take 78,000 years. That is longer than the span of all recorded human history. Every empire that has risen and fallen, every language invented and lost, every monument built and buried by sand, it all fits inside a fraction of that time scale. At New Horizons speed, we would be crawling like ants across a desert, so wide that even civilizations would wither to dust before the first footsteps crossed it. This is the paradox of our nearest star. It is close enough to tempt us, close enough to whisper possibilities about new worlds, maybe even new life. Yet it is far enough to mock us, to show us how small and slow we really are. Every rocket ever built, every fuel we've burned, every ounce of speed we've clawed from physics, all of it leaves us stranded in our cosmic cradle. We can look across the gap, but reaching it is another story entirely. And that's where the nightmare begins. Because the distance is just the first problem. Beyond the yawning emptiness, the blackness itself becomes hostile. Radiation, dust, physics, and time all conspire against us. The universe doesn't just separate us from Proxima Centauri, it builds a gauntlet of death between here and there. And yet, despite everything, the human mind keeps staring at that distant point of light, wondering what it would take to cross the gulf. Could we do it with technology we don't yet possess? Could we endure the years, the radiation, the silence? Or is the dream of touching another star destined to remain just that? A dream. These questions are not science fiction. They are the ultimate test of what it means to be human. Because when we talk about Proxima Centauri, we aren't really talking about a distant star. We are talking about the limits of imagination, the boundaries of survival, and whether our species can ever break free from the small patch of universe we were born into. When scientists say Proxima Centauri is only 4.2 light-years away, It sounds deceptively comforting, as though the gap between us and our nearest stellar neighbor is small enough to bridge if we just tried hard enough. But only is one of those words that disguises the terror of reality, because in human terms, 4.2 light-years is not close. It is a distance so crushingly large that our language breaks when we try to explain it. A light-year is nearly 6 trillion miles, and multiplying that by 4 gives you a number so absurd that even writing it down 25,000 miles does nothing to make it easier to grasp. Numbers that big don't mean anything until you scale them into something your imagination can process, and when you do, the illusion of closeness collapses into horror. Imagine shrinking the Earth to the size of a marble and placing it on a street corner in New York. Now shrink Proxima Centauri to the same size and place it, not in Boston, not in Los Angeles, but in the middle of the Pacific Ocean. Between them lies nothing but water, nothing but void, no stepping stones, no islands, just a gulf, so immense it swallows everything. That's the reality of next door in the cosmic sense. Proxima feels close only because the rest of the stars are unimaginably farther away. Compared to the galaxy itself, yes, it's nearby. But compared to anything humans have ever achieved, it's impossibly, laughably distant. We can measure the futility of this distance with the machines we've already built. NASA's New Horizons probe, one of the fastest spacecraft ever launched, screamed out of the solar system at 36,000 miles per hour. It reached Pluto 3 billion miles away in less than a decade. That was considered a triumph of engineering. But at that same speed, the trip to Proxima Centauri would take 78,000 years. Imagine the scale of that timeline. 78 millennia ago, humans lived in caves, painted animals on stone walls, and fought to survive against Ice Age predators. Civilization, agriculture, writing, the wheel, electricity, none of it existed. And that is how long it would take New Horizons to reach our nearest neighbor. Not one lifetime, not 100 lifetimes, more than the entire span of recorded human history. But it gets even more absurd when you scale it down to personal terms. Let's say you wanted to walk the distance at a steady 3 miles per hour, no sleeping, no eating, just a ceaseless march. To cover the 25 trillion miles, you would need over 1 billion years. You would die long before your first fraction of progress even registered against the immensity of the journey. Driving doesn't help. At highway speeds of 60 miles per hour, the trip would take 350 million years. If you somehow managed to survive the road trip, you would watch the sun orbit the center of the Milky Way 1.5 times before you finally pulled into Proxima's neighborhood. Even the fastest jet humans have ever built, racing at 600 miles per hour, would still need 4.7 million years to make it. For comparison, Homo sapiens, the species you belong to, has only existed for around 300,000 years. That means the fastest plane in history would take 15 times longer than the entire existence of modern humanity. And still we call this close. It's a trick of perspective, the same way someone might say Mount Everest is just a short walk away on a map, ignoring that the walk is vertical, deadly, and impossible without oxygen. Proxima Centauri is not a friendly neighbor we can casually visit. It is the barest whisper of hope across an ocean designed to drown ambition, and yet that's exactly why it captures our imagination. Because when we look up at the night sky and realize that every other star is even farther, Proxima becomes a symbol. It is the nearest door out of our solar system, the first threshold into the wider galaxy. It mocks us with its inaccessibility, but it also dares us to dream. And humanity has never been good at backing down from a dare. If the distance alone were the only problem, maybe, just maybe, humanity could find a way to endure the centuries, to build machines that crawl through the abyss, and eventually arrive, but the universe has never been so kind. Space is not a peaceful highway stretching silently between stars. It is more like a battlefield, a gauntlet of invisible dangers, waiting to punish anything foolish enough to venture too far from home. To call it empty is misleading. Space is full of killers, unseen radiation, microscopic dust, and storms of energy that can shred even the most advanced spacecraft long before it ever approaches its destination. Start with the radiation. Beyond the protective bubble of Earth's atmosphere and magnetic field, astronauts are bombarded by cosmic rays, high-energy particles fired across the galaxy by exploding stars. These particles don't just pass by harmlessly, they smash into cells, rip apart DNA, and leave behind damage that the body struggles to repair. For someone traveling to Proxima Centauri, this isn't a temporary hazard, it's a death sentence stretched over years. Imagine getting the equivalent of a full-body CT scan every single day for the entire length of the journey. That's what cosmic rays would do to the human body. Cancer, radiation sickness, organ failure. It would all arrive long before the ship even left the outer edge of our solar system. And radiation isn't the only assassin hiding in the void. There is also the threat of cosmic dust. Tiny particles, fragments smaller than grains of sand, drift endlessly between the stars. At human scales, they are microscopic, harmless. But scale up the speed to a spacecraft, moving at even 10% of light speed, and each particle becomes a bullet, a high explosive warhead with the energy of a grenade. Imagine traveling through space and colliding with something invisible, something so small you couldn't even see it coming, and yet the impact is powerful enough to tear through metal like paper. A pebble-sized fragment would strike with the force of a bomb, instantly shredding the vessel and everything inside. There are billions of cubic miles between us and Proxima Centauri, and over such vast distances, the odds of hitting something are not just possible, they're nearly guaranteed. Then there are the storms. Our own sun, a relatively calm and stable star, occasionally unleashes solar flares that force astronauts on the International Space Station to retreat into shielded compartments. These events send torrents of charged particles screaming through space at millions of miles per hour. Now imagine being exposed to such storms, with no shelter, no planet-sized magnetic field to deflect the radiation. A major solar storm could fry electronics, knock out power systems, and kill the crew in hours. And that's just our sun. Other stars, like Proxima Centauri itself, are far worse, capable of eruptions so violent that they make our solar storms look like gentle breezes. For a spacecraft, these hazards create a nightmare of engineering problems. Shielding against radiation requires enormous amounts of material, thick layers of water, metal, or lead, yet every pound of extra mass multiplies the fuel requirements for propulsion. Protecting against dust impacts means either building shields thicker than tank armor or inventing some kind of energy field to deflect particles before collision. Both solutions make the ship heavier, slower, and even less practical. It becomes a brutal paradox. Protect the crew and you make the trip impossible. Leave them unprotected and they die before they reach the halfway mark. And through all of this, the void remains silent, cold, and endless. No landmarks, no pit stops, no opportunities to rest or repair. If something breaks, it stays broken. If food supplies run short, there are no resupply missions. If the systems that recycle air and water fail, the crew suffocates or starves in the dark. The void offers no mercy, no second chances. This is the hostile truth of interstellar travel. The distance is terrifying enough, but the environment itself is worse. It doesn't simply separate us from Proxima Centauri, it actively fights us, punishing every attempt to cross it with radiation, dust storms, and silence. And yet, even if we somehow survived these dangers, another wall stands in our way. The speed trap, because in space, the faster you try to go, the harder the universe pushes back. When you imagine traveling to Proxima Centauri, you might think the solution is simple: just go faster. After all, we've gone from horse-drawn carts to supersonic jets in only a few centuries. Surely, scaling up to interstellar speeds is just a matter of pushing harder on the accelerator. But space doesn't work like that. The faster you try to move, the more the universe itself resists. And the cruel truth is that even our greatest achievements in speed are laughable against the backdrop of the stars. Voyager 1, the farthest human-made object from Earth, has been flying since 1977. It now cruises through interstellar space at roughly 38,000 miles per hour, fast enough to circle the Earth in just 40 minutes. That sounds impressive until you compare it with the challenge ahead. At that speed, Voyager would still need over 70,000 years to reach Proxima Centauri, assuming it were even heading in the right direction. The Parker Solar Probe, currently the fastest spacecraft ever built, reached a blistering 430,000 miles per hour by slingshotting around the Sun. That's 12 times faster than Voyager, yet even at this record-breaking speed, the trip to Proxima would still take over 6,000 years. For perspective, that is longer than the time since humans first invented writing. We celebrate these engineering triumphs, and rightly so, but in cosmic terms, they're nothing more than baby steps. The barrier is not just technological, it's physical. Every spacecraft we've ever built relies on fuel, and here lies the vicious cycle. The more fuel you load, the heavier the spacecraft becomes. The heavier it becomes, the more fuel you need to accelerate it. This spiral quickly becomes absurd. The space shuttle, for example, weighed 4.4 million pounds at launch, but could only deliver about 50,000 pounds into orbit. In other words, 94% of its mass was just fuel and engines, leaving only 6% for useful payload. Scale this up to interstellar travel, and the math falls apart. Even if you filled an entire planet with fuel, it still wouldn't be enough to push a meaningful spacecraft to a decent fraction of light speed. And this is where the energy wall rises in front of us. Accelerating just 1 ton of mass to 10% of light speed, considered the bare minimum for practical interstellar travel, requires nearly a quintillion joules of energy. That's 900 billion joules, more than the total yearly energy consumption of the entire human race, thousands of times over. And that assumes perfect efficiency, which doesn't exist. Real engines waste vast amounts of energy as heat, exhaust, or radiation. Factor that in, and the numbers swell even further into impossibility. And remember, once you get there, you have to slow down. Otherwise, your spacecraft just screams past Proxima in minutes, unable to stop, rendering the entire journey meaningless. That means doubling the energy budget, an equation so staggering it borders on absurd. The more you crunch the numbers, the clearer the trap becomes. Our rockets, brilliant as they are crawling ants in a universe built for cheaters. Chemical propulsion, ion drives, even the fastest probes we've ever launched. All of them are hopelessly outmatched by the challenge of interstellar travel. It's not just a matter of engineering bigger rockets, it's a matter of confronting the fundamental limits of physics and energy. Going faster means fighting against inertia, against mass, against the square law of velocity that multiplies energy requirements until they break every calculator. This is the cosmic speed trap, the barrier that turns just go faster into a cruel joke. The universe doesn't allow shortcuts, and the very laws of physics mock our ambitions. Yet humans are nothing if not stubborn. Faced with impossible numbers, we've started to dream of impossible solutions. spacecraft powered by sunlight, engines driven by nuclear bombs, sails the size of cities, and even the perfect fuel of antimatter. These ideas sound like science fiction, but they might be the only way forward. Because if rockets can't break the trap, maybe something stranger can. When conventional rockets fail us, the human imagination does what it always does. It leaps. If we can't crawl across the void using chemical fire, then maybe we can ride beams of light, detonate nuclear bombs behind us, or even harness the most destructive substance in existence, antimatter. These ideas sound like science fiction, but they are the desperate visions of scientists and engineers who have stared into the abyss of interstellar distance and refused to accept the word impossible. Each concept pushes the boundaries of physics and engineering to their breaking point, offering glimpses of what might one day carry us to Proxima Centauri. The first dream is the solar sail, a spaceship pushed not by engines but by light itself. Sunlight may feel weightless on your skin, but photons carry momentum, and when they strike a reflective surface, they push ever so slightly. A solar sail is essentially a mirror stretched across space, as thin as spider silk and as wide as a city. The sail unfurls, and sunlight begins to push it forward, gently, almost invisibly, but without fuel, without limits. The pressure is so weak that it would take a square mile of sail just to move a few pounds. But in the vacuum of space, with no friction, even the smallest nudge adds up. Over weeks, months, and years, the sail can accelerate to incredible speeds, theoretically reaching 1/10 of light speed. The challenge is size and fragility. These sails would need to be thinner than human hair, stretched across tens of miles, and perfectly aligned for decades, while being shredded by micrometeoroids and cosmic radiation. One tear, one wrinkle, one misalignment, and the dream is over. And yet, the elegance of a ship flying on sunlight has kept the idea alive, inspiring projects like Breakthrough Starshot, which imagines fleets of gram-sized probes pushed by Earth-based lasers to 20% of light speed. Another vision is more explosive, literally. In the 1960s, a project called Orion explored the wild idea of nuclear pulse propulsion. The design was brutal and simple: drop nuclear bombs out the back of a spaceship, detonate them, and ride the shockwaves. Each blast would slam into a massive steel plate, connected to the ship by shock absorbers, kicking it forward like a cosmic pogo stick. Theoretically, this could accelerate a ship carrying people and supplies to 1/10 of light speed, making interstellar travel possible within a human lifetime. The drawbacks: everything else. The spacecraft would essentially ride a chain of nuclear detonations, bathing itself and its crew in lethal radiation. The pusher plate would endure hundreds, maybe thousands of nuclear blasts without disintegrating. And on top of the engineering nightmare, there's the small matter of detonating nuclear weapons in space, something the world has already outlawed. Orion was shelved, but the idea lingers as one of the few propulsion concepts with enough raw power to make the journey plausible. And then there is antimatter, the holy grail of propulsion. When matter and antimatter meet, they annihilate completely, releasing pure energy according to Einstein's famous equation, E=mc². No fuel is more efficient, no reaction more powerful. A gram of antimatter colliding with a gram of matter would unleash energy equal to 43 kilotons of TNT, several times the Hiroshima bomb. Just a few ounces could send a ship hurtling toward Proxima at a fraction of light speed. But antimatter is not something you scoop up at the gas station. Creating it requires particle accelerators that consume more energy than they produce. Right now, we can only manufacture antimatter in quantities so tiny they would barely boil a cup of water, and storing it is an even greater nightmare. Let it touch the walls of its container, and it annihilates instantly. Magnetic traps might hold it, but any failure would vaporize the ship in a flash. It is the perfect fuel if we can ever control it. Other ideas verge on the fantastic. The Bossat ramjet, for example, imagines a ship with a magnetic scoop, miles wide, collecting hydrogen from the interstellar medium and fusing it into helium to power the ship forward. In theory, the faster you go, the more fuel you collect, accelerating endlessly until you skim the edge of light speed. In practice, the interstellar medium is so thin that scooping enough hydrogen would be like trying to power a car by catching raindrops while driving through a desert. Worse, the drag from the scoop might actually slow the ship instead of speeding it up. Every one of these propulsion dreams comes with challenges so daunting they border on fantasy. And yet, they represent our only hope of breaking free from the speed trap. Because rockets cannot carry us to the stars, but perhaps sails, explosions, annihilation, or fusion can. Still, even if we solved propulsion, we would run headfirst into another barrier, ourselves. The human body, fragile and mortal, was never meant to endure the journey. The next problem is not the machine, but the people inside it. Even if humanity found a way to cheat physics and engineer a propulsion system powerful enough to cross the void, one obstacle remains more fragile, more unpredictable, and infinitely more complicated than any machine us. The human body, evolved for the gentle cradle of Earth, is not designed to survive the brutal emptiness of interstellar space. Radiation, time, psychology, and biology all conspire to make us the weakest link in the journey to Proxima Centauri. The first enemy is invisible. Beyond Earth's protective atmosphere and magnetic field, cosmic rays stream through space like bullets fired from ancient stars. These high-energy particles carry enough force to tear through DNA, shattering the instructions that keep our cells alive. Astronauts on the International Space Station are already exposed to doses of radiation far above what is safe on Earth, and that's while orbiting a mere 250 miles above the surface. A crew venturing to Proxima Centauri would face years of constant bombardment, the equivalent of receiving a full-body CT scan every single day. Cancer, organ damage, infertility, even neurological breakdowns, all would arrive long before the destination. Shielding against this radiation would require walls several feet thick, made of lead, water, or other dense materials. But adding such mass multiplies the fuel requirements, dragging the mission back into the impossible. Even if radiation could somehow be mitigated, time itself becomes the next killer. A trip lasting thousands of years cannot be made by one crew. Generational ships, vast habitats carrying entire populations have been proposed. The idea is simple: if the crew can't survive the journey, then their children, grandchildren, and great-grandchildren will. But the simplicity ends there. Imagine being born inside a metal cylinder, never seeing a sky, never feeling wind, never walking on soil. Your world is corridors and artificial lights, recycled air and hydroponic farms. You did not choose the mission, you inherited it. For you, Proxima is not a dream, it's a prison sentence written before you were born. Entire generations would live and die inside the ship, their only purpose to keep the vessel moving toward a star they might never see. The psychological toll of such an existence could shatter entire societies. Factions could form, conflicts could erupt, and over centuries, the very idea of the mission could be forgotten. Imagine great-grandchildren of the original crew asking why they must continue at all, why they shouldn't turn back, or simply abandon the journey in favor of building a permanent home inside the vessel itself. A generational ship is not just an engineering problem, it is a sociological experiment of terrifying scale. Some propose a more elegant solution: hibernation. If humans could be placed into suspended animation, their metabolism slowed to a crawl, they could sleep through the centuries and awaken at their destination. The concept has roots in nature. Bears, bats, and even small mammals endure long winters by dropping their body temperature and conserving energy. But applying this to humans is a different matter. Medical science has achieved hypothermia-induced stasis for hours during surgery, but never for decades or centuries. The risks are immense. Cooling the body for too long triggers organ failure, clotting, or irreversible brain damage. Even if such systems were perfected, the crew would awaken weakened, muscles atrophied, bones brittle from years of inactivity. They would need time to rehabilitate at precisely the moment they were required to perform at their peak. And what if the systems failed mid-journey? A broken hibernation pod halfway to Proxima is not a malfunction. It is a coffin. Then there is the cruel trick of relativity. As a ship approaches significant fractions of light speed, time itself begins to warp. To the crew, the journey might feel shorter, weeks or months, trimmed away by time dilation. But back on Earth, years or decades pass. A traveler leaving today could arrive at Proxima, feeling only a few years older, but everyone they knew on Earth would have aged decades. Their children would be adults, their friends old or dead, their culture unrecognizable. In effect, they would return not just as explorers, but as exiles in time, cut off from the world that sent them. The mission might succeed physically, but fail emotionally, turning pioneers into strangers in their own story. These are the human problems: radiation that kills the body, time that fractures societies, psychology that corrodes purpose, and relativity that warps connection. No propulsion breakthrough, no engineering marvel can erase these truths. Even if we master machines, we must still master ourselves. And yet, all of these challenges pale before the final insult. Even if we somehow survive the journey, the destination itself may already be waiting to kill us. Proxima Centauri, our so-called hope, is a star that seems to hate life. For all the talk of reaching Proxima Centauri, few people pause to ask an uncomfortable question: what exactly is waiting for us when we get there? We tend to imagine a second Earth, a welcoming world bathed in gentle starlight, oceans glistening, and forests swaying under alien skies. But the truth is far harsher. Proxima Centauri is not like our Sun. It is a red dwarf, smaller, cooler, and infinitely more violent. If our star is a calm, steady hearth, Proxima is a furnace that burns with fits of rage, spewing storms so intense they make our solar flares look like sparks from a campfire. This is the star we dream of reaching, and it is less a neighbor than a cosmic tyrant. Red dwarfs burn their fuel slowly, giving them lifespans measured not in billions, but in trillions of years. In theory, that sounds ideal for life, a stable energy source for incomprehensible stretches of time. But that stability hides a curse. Red dwarfs never really calm down. They remain hyperactive, constantly releasing bursts of energy and radiation. Proxima Centauri, in particular, unleashes stellar flares that can multiply its brightness tenfold in minutes, flooding its system with lethal doses of ultraviolet and X-ray radiation. For any spacecraft approaching, a single mistimed flare could fry electronics, strip shielding, and kill a crew in an instant. For any planet in orbit, it is an endless bombardment. And orbiting close to this furnace is Proxima b, the so-called Earth-like world that sparked headlines around the globe. It is rocky, similar in size to our planet, and lies within the habitable zone, the narrow band where liquid water could, in theory, exist. On paper, it looks like a second Earth. In reality, it may be a nightmare. Proxima b circles its star at a distance of just 4 million miles, 20 times closer than Earth orbits the Sun. At that range, the planet is almost certainly tidally locked, meaning one side faces eternal day, while the other side lies in permanent night. The day side, blasted by constant radiation, could be scorched into a desert of molten rock, while the night side freezes into a wasteland of ice colder than Pluto. If habitability exists at all, it would be in the thin twilight zone between fire and ice, a narrow strip where temperatures might allow liquid water. But even there, the conditions would be brutal. Winds would scream across the planet as hot air from the day side rushed to the frozen night side, creating permanent storms of unimaginable ferocity. And then comes the problem of atmosphere. Billions of years of relentless flares and stellar winds from Proxima Centauri may have stripped Proxima b bare. Without a strong magnetic field, any air it once had could have been blown into space long ago, leaving the surface naked and exposed. Without an atmosphere, liquid water cannot exist, and life as we know it is impossible. Some scientists speculate that if Proxima b does retain an atmosphere, it is likely toxic or unstable, filled with greenhouse gases or exotic chemicals that would choke human lungs and corrode machinery. Even if a ship somehow arrived in orbit, and even if explorers managed to land safely, every moment on the surface would be a battle. Radiation storms would strike without warning, forcing colonists underground or beneath oceans to survive. The eternal day side would be unlivable, the eternal night side equally hostile. The twilight strip might offer temporary refuge, but under skies filled with auroras from stellar bombardments and hurricanes roaring endlessly, it would hardly resemble paradise. At best, Proxima b might sustain microbial life in its oceans or beneath its crust. At worst, it is a barren husk, sterilized again and again by the wrath of its star. And yet, despite all of this, Proxima Centauri holds our imagination hostage. Because it is there, because it is close, because it is the first step beyond our solar system, we cannot stop dreaming about it. Maybe life finds a way in places we cannot yet imagine. Maybe underground oceans shelter something alive, something waiting to be discovered. Or maybe Proxima b is a warning, a reminder that not every neighbor is friendly, not every world is a home. Whatever the case, reaching it will not solve our problems. It will multiply them, but if the destination is hostile, why do we keep talking about it? Why dream of a journey so dangerous and futile? The answer lies not in Proxima itself, but in us. After hearing the staggering distances, the lethal radiation, the impossible engineering problems, and the hostility of Proxima Centauri itself, the logical conclusion seems obvious: give up. Why chase a star that does not want us, a destination that offers nothing but storms and emptiness? And yet, that is not how humanity thinks. We are drawn to the impossible, compelled by challenges that seem designed to break us. The very fact that Proxima Centauri looks unreachable is precisely why we cannot stop staring at it. Because beyond the physics and the danger lies something deeper, the question of survival itself. Our planet has nurtured life for billions of years, but it has also erased it again and again. Extinction is not an exception, it is the rule. The dinosaurs ruled Earth for over 160 million years, longer than our species has even existed, and yet their reign ended in a single day when a rock from space slammed into the Yucatan Peninsula. The skies darkened, the climate collapsed, and their empire vanished almost overnight. If it happened once, it can happen again. Another asteroid, another supervolcano, another cosmic burst of radiation from a nearby star. It takes only one catastrophe to wipe the slate clean. And in that sense, the dream of Proxima is not about curiosity. It is about insurance. If humanity remains chained to a single world, then our survival rests entirely on the stability of one fragile planet. But if we scatter among the stars, no single disaster can erase us. This is the core of the madness. We dream of Proxima Centauri, not because it is kind, but because it is there. It is the closest stepping stone out of our cradle, the first rung on the ladder that leads from planetary species to interstellar civilization. And history shows that the impossible has a strange way of becoming inevitable. Once, powered flight seemed ridiculous. The idea of men soaring through the sky was fantasy until two brothers with a wooden contraption proved otherwise. Once, walking on the moon belonged to myth, yet within a lifetime we planted flags in lunar dust. The pattern is clear. What one generation calls madness, the next calls progress. Proxima may look unreachable today, but what about in a century or 1,000 years? Technology does not just advance, it accelerates, turning impossibility into inevitability. But beyond survival and beyond technology, there is something more intimate pulling us forward: the human hunger for meaning. We are not content to simply exist. We climb mountains, not because we need to, but because they stand in front of us. We dive into oceans, cross deserts, and sail into storms, chasing horizons for no reason other than to know what is on the other side. The journey to Proxima Centauri is the ultimate horizon, the most distant frontier our imaginations can grasp. To attempt it would be to declare that we are more than our fears, more than our limits, that we belong not just to Earth, but to the cosmos itself. Yes, the dangers are real. Yes, the odds are crushing. But to stop dreaming of Proxima would be to deny the very thing that makes us human. We are not the strongest species, nor the fastest, nor the most resilient. What makes us extraordinary is our refusal to accept boundaries. The journey to another star is less about physics and more about identity. It asks us to decide what kind of species we want to be. One that waits for extinction, or one that risks everything to spread across the stars. And this is why, despite the madness, the dream endures, because Proxima Centauri is more than a star. It is a test, a mirror, a challenge, written in the night sky. It asks us whether we are content to stay home forever, or whether we dare to become something more. And if history is any guide, humanity has never been content to stay home, which leads to the final truth. The impossible journey to Proxima Centauri is not really about reaching another star at all. It is about proving that we can. So here we are, standing at the edge of imagination, staring across the gulf at a star that seems both tantalizingly close and impossibly far. Proxima Centauri, our so-called nearest neighbor, mocks us with its distance, its violence, and its indifference. The numbers alone are crushing: 25 trillion miles, thousands of lifetimes in a single voyage, radiation storms that could sterilize entire planets, and propulsion challenges that make even our greatest rockets look like toys. Everything about the journey screams that it cannot be done, and yet, somehow the impossibility is exactly what makes it irresistible, because hidden beneath the physics and the terror is a deeper truth. We are a species built for reaching beyond what seems possible. Think about it. Our ancestors once huddled in caves, terrified of the dark sky above them. Then they painted the walls with visions of animals and gods, lifting their gaze upward. Centuries later, they built ships to cross oceans that seemed endless, guided only by the stars. When the seas were conquered, they looked to the sky itself, inventing machines that defied gravity. When the sky no longer sufficed, they built rockets that clawed their way into orbit. Each step looked like madness at the time. Each step was declared impossible by skeptics who could not see past the limits of their moment. And yet, step by step, we turned the impossible into history. The journey to Proxima Centauri is simply the next step on that same ladder. It is bigger, yes, and more terrifying, yes. But it follows the same pattern. Today, we see only the problems, fuel equations that don't add up, radiation doses that seem fatal, distances that dwarf the span of civilizations. But tomorrow, or in 100 tomorrows, or 1,000, someone will find a way, because that is what we do. We break boundaries, we solve problems, we risk everything for the chance to go farther than before. And make no mistake, this is not just about curiosity or exploration, it is about survival. Earth is generous, but it is not eternal. Asteroids, supervolcanoes, gamma-ray bursts, even our own reckless hands, all threaten to erase us if we stay bound to a single fragile world. The dinosaurs ruled for millions of years, and still a rock from the sky ended them in an afternoon. To remain here, clinging to one planet, is to play a game with cosmic dice, and eventually the dice will come up against us. But if we can spread to the stars, if we can scatter ourselves across light years, then no single catastrophe can wipe us away. Interstellar travel is not just ambition, it is insurance for everything we are and everything we could be. And beyond survival, there is meaning. To reach another star is to declare that humanity belongs to the universe, not just to Earth. It is to prove that we are more than clever animals scrambling for food and shelter, that we are capable of shaping our own destiny against impossible odds. Imagine what it would mean, generations from now, for a human child to look up at the red light of Proxima Centauri and know that their ancestors crossed the void to stand there. Imagine the stories, the art, the perspective that would emerge from a civilization no longer bound to one star, but stretching across many. It would not just change our science, it would change our souls. So yes, the journey to Proxima Centauri looks impossible today, but so did flight, so did the moon, so did everything until the moment it wasn't. The impossible has always been the doorway through which humanity steps into its future, and perhaps, in the cold, distant glow of Proxima, we can see not just a hostile star, but an invitation, a challenge written in fire and distance, daring us to try, because in the end, the journey is not about Proxima at all. It is about us, about proving that we are a species that does not accept limits, that does not bow to fear, that refuses to let extinction be our story. One day, whether in a century or 1,000 years, a human-made vessel will arrive at Proxima Centauri. It may not carry us, but it will carry our ambition, our creativity, and our refusal to quit. And when that day comes, it will mark not just a triumph of science, but a declaration that humanity has graduated from a planetary species into a cosmic one, that we have claimed our place among the stars. Until then, we look up at the night sky, at the faint light of Proxima shining across 4 years of emptiness, and we keep dreaming. Because the dream itself is the first step toward making the impossible inevitable.